Hello. In this video, we're going to be discussing exponential functions. This begins the chapter on exponential and logarithmic functions, which are some of my favorite things to study. There can be a lot of fun, but there are a lot of little details that you'll have to remember. So we're going to get started with exponential functions in the first section, 6.1. Let me share my screen with you, and we'll go through some of the basics. So one of the things we want to talk about is the difference between an exponential function and some of the other kinds of functions that we've been talking about. So we're going to start comparing two different types of functions. The first one is an exponential, and you'll see it right here. This is f of x equal to 2 to the x, this function right here. That function is an exponential function, and we know that because we have a constant number that is greater than 0, which is 2, and not 1, and it's being raised to a linear function of the variable x, right? So that makes it an exponential function. Now, the other function is a line. So when we look at the other one, we have a line. So we have an exponential on the left, which we'll define a little bit better in a few minutes, and this is a linear function. And when you take some values from the x-axis and you allow those to be your input values that you see here on the left, then we can go ahead and we can multiply the variable x by 2 to get these values coming out for the linear function. And you can see that the values are basically increasing by 2. That's because it's linear, which means you're always adding the same value every time when you increase by 1 unit on the x, or you're subtracting the same value every time when you're decreasing by 1 unit on the x. The exponential is very different. Notice that as x increases by 1 each time, the value for y increases by double. So it's going from 1, then it doubles to 2, then it doubles to 4. So here we would have added 1, but here we add 2, then we add 4, then we add, 8. You can tell right away that it's not linear. We're not adding the same value every time we increase the x variable by 1 unit. So this is what we mean by an exponential. It grows much faster. You can tell that after we've had changes in x from 0 to 6, the exponential is up here at 64, while the linear is still down here at 12. And in fact, the next values would be 128, 256, 512. Then it goes to 1,048 and 2,096. I mean, it really jumps incredibly fast. And this is what is often meant by exponential growth. Now, if we're to plot these, you can see them here on this graph. So here's the graph of y equal 2 to the x in the black, and you can tell that it's approaching the x-axis as it goes to the left, where the x values are all negative. And that sort of makes sense, because if the x is negative, we have a negative in the exponent, which basically means that it goes to the denominator. So we have 1 over 2 to the x, which gives us fractions, but it never gets to 0 because the base is a positive value of 2, not 0. We can't get 0 coming out of an exponential function. It's just impossible. However, if you look at the linear function, it is possible to get 0. In this case, because the function is y equal 2x, you get 0 when x is 0. And you can tell that they're both going off to infinity as you move to the right, but as you move to the left, they're very different. The linear continues to go down forever, so it approaches negative infinity as we go to the left, but the exponential flattens out. Never goes truly horizontal. It continues to get lower and lower, but it never gets to 0. You may say, well, how's that possible? Well, the values that are coming over here are numbers like half, and then we take half of the half and we get a fourth, and then 1/8, and then 1/16, and then 1 over 32, 1 over 64. We're basically getting the reciprocal of these right here. And so then it gets lower and lower, but you can tell that because the numerator is always 1, it never actually goes to 0. So this is the difference between an exponential and a linear. Linear is a line, right? Linear for line. Exponentials kind of look like this, all right? So I don't know, it's sort of a, I don't know, it's a pose from ballet. So it looks like this. So one arm is curving and going up and the other is curving and going down and approaching the x-axis one way or the other. All right, let's take a little bit finer look at the graph of y equal 2 to the x. And you can see that I've plotted the different values here so that you can tell what they are. Notice that when x is 0, then 2 to the 0 gives us the number 1. So we can expect on many exponential functions that don't have a coefficient that they're going to go through the point 0, 1. This is very, very common, right? Now, you can also tell that as it goes to the right, as the x values increase, because it is a constant 2 raised to that power, the numbers go up very, very rapidly. As we go to the left and the x values are negative, and negative power means reciprocal. So remember that if I have 2 to the negative 2, this is the same as 1 over 2 squared, which becomes 1 over 4. A negative exponent just changes position. Because it's written in the numerator, we change it to the denominator, and then we get the fraction 1 over 4. Now, what if we started with a number? Again, the number has to be greater than 0 and cannot be 1. What if we start with a fraction like 1/2? Well, this gives us an exponential, but instead of increasing as we move to the right, it's decreasing. You can see this blue graph is coming down. So it's almost like we took this picture that we have on the left and we flip-flopped it across the y-axis, and now it's coming down. Now, how does that happen? Well, remember, if we can write a negative exponent as 1 over that to the positive power, then we can write 1 over 2 as 2 to the negative 1 raised to the x. And then because we have 1 base 2 and 2 powers, we multiply the powers and we get 2 to the negative x. Now remember that when you multiply x by a negative inside the function notation, it does reflect the graph across the y-axis. So from here, we get to here, right? So let's now take a look at the actual definition of an exponential function, which we have right here in the center. And sometimes we're allowed to have a coefficient. So let me give you 2 examples. This time I'm going to go with 3 to the x, which grows even faster than 2 to the x because the base is larger. Now, the 3 here is called the base. So this is the base. And this is the power. And this, of course, would be the answer part. And the power we can also call the exponent, right? Okay. So we take the base, we raise it to the power, we get the answer. Now, the base has to be strictly greater than 0 and not equal to 1. Now, why wouldn't we allow 1? What is 1 to the first power? 1. What's 1 to the second power? 1. 1 to the third power? 1. What's 1 to the 0th? 1. What's 1 to the negative 1? 1 over 1 to the first, which is still 1. What's 1 to the negative 2? 1 over 1 squared, which is still 1 over 1, which is still 1. In other words, it just gives us the horizontal line y equal 1, which does not look like the other exponentials that have this sort of behavior. So we eliminate the possibility that the base can be 1 because it's just the boring old y equal 1 horizontal line. All right, now why do they have to be greater than 0? Well, we want them to be defined for all values of x. So we want them to be defined for x from negative infinity to infinity. And we have a problem. If we allowed the base to be a negative, let's just pretend this is utterly wrong, right? So let's label this wrong. If I took negative 2 and I raised it to the x power, what would happen if the power with something like 1/2. If the power is 1/2, the 1/2 power becomes the square root. And this would give me the square root of a -2, which is I square roots of 2. That means that it's not real, right? It exists, it's a number, it's just an imaginary number, it's not a real number. And we want all of our values to be real. So because this can happen with any fractional power with an even denominator, when you reduce the power, then we will not allow our negatives to be bases, right? Now the power can be negative, but the base has to be positive, right? So we're not going to do this here. We're going to force the base to be strictly greater than 0. And because of that, because the base is strictly greater than 0, that means we can't get a negative for the answer. So because the base is strictly positive, the answer is also strictly positive. The only thing that can be negative or 0 is the power, right? Okay, now let's take a look at these other things here. Notice that they have f of x equals ab to the x. So we can actually have another function, f of x, or you can write y, equal 2 times 3 to the x. Now, you need to put some kind of symbol between the 2 and the 3, otherwise it looks like 23. Personally, when I do these, I like to put the exponential part in parentheses because the exponent has to be done first before you can multiply by the 2. That's the order of operations. So in this particular case, if we had x equals 0, 3 to the 0 is 1, but instead of going through the 0.01, because it's multiplied by a 2, it'll actually go through 0, 2. Now the a can be any real number, all right, but it can't be 0. If it's 0, then we really just have y equals 0. So a can be any non-zero real number, and we call it the initial value. Why the initial value? Well, if x is 0 and we were pretending x was time, then t equals 0 is the initial value. And any positive value raised to the 0th power is the number 1. The only number we have a problem raising to the 0th power is 0. 0 to the 0th is something we call indeterminate. You'll get into that in calculus if you go that far. Now, the b, again, has to be a positive number and not 1 because that just gives us the boring horizontal line. The domain, that's the power, x can be anything. X is in, so that symbol right there means is an element of. The interval from -infinity to infinity. The range y is all positive numbers if a is positive. Now, if a were negative, then it would change everything to being negative. So it would sort of flip over the x-axis and it would be rotated down, right? So it could look kind of like this, something like that. The y-intercept is going to be 0 times a, and the horizontal intercept, again, is going to be that x-axis, unless we shift it up, down, left, or right, which of course we can do. We shift it up or down, then whatever amount we shifted up, that's going to become the new horizontal asymptote. And we'll see that in the section when we discuss the graphs of exponential functions. For now, what I want to do is I also want to talk about what's called exponential growth. Now, exponential growth is a particular way of looking at an exponential function. Now, when we're looking at this right here, remember, a is any real not equal to 0. And b has to be strictly positive because we don't want square roots of negatives. And it's not 1 because that would just be boring, right? And x can be anything, -infinity to infinity, right? These are our restrictions for exponential functions. Yes, you need to memorize it, and you need to memorize it really, really well, because we're going to be using it constantly throughout this entire chapter. Now, ab to the x, when x equals 0, then b to the 0 equals 1. So we get f of 0 equals A times 1, which equals A, which is the ordered pair 0, A. And that's what we mean by the initial value. We tend to call whenever the independent variable is 0, the initial value, the starting point. B is actually the amount we're growing by. It's the growth factor, the growth multiplier per unit of X. Let's look back up here at our table. Notice that we have this power 2 raised to the X power. That means our growth factor is 2, and there is no coefficient, so it's an understood positive 1. And notice that when we move from one Y value to the next, the growth factor is multiplying by what was there previously by 2. So we're getting 1 times 2, 2 times 2, 4 times 2, 8 times 2, 16 times 2, because the growth factor is 2. If we had 3 to the X, the growth factor would be 3. So we would start with 1, then 3, then 9, then 27, then 81, 243. Yikes. What's the next one? 729, I think. All right. Let's now move on and start looking at some of the homework problems. So in this first homework problem, what we want to do is we want to try to figure out if something is exponential or if it's linear. Now, if it's linear, remember that you are adding the same value every time, each time the independent variable increases by 1. So when X goes from 1 to 2, you add 5. When X goes from 2 to 3, you add another 5. When X goes from 3 to 4, you add another 5. It's always the same amount. Or you're subtracting. When X goes from 1 to 2, you subtract 7. When X goes from 2 to 3, you also subtract 7. When X goes from 3 to 4, you subtract 7 again. Now that does not happen in an exponential. In an exponential, we have this multiplicative factor. So when we're looking at them, we can sometimes tell, oh, I see that each time X increases by 1, I'm multiplying by 2 each time, or I'm multiplying by 1/2. And that would be your multiplicative factor. The other way of thinking about it is that exponential functions are actually increasing by a percentage of what was there before. So if you have a 1/2 multiplicative factor, then that's 50%. So you're increasing by 50% each time. So what you're doing, or decreasing by 50% each time. So when you're looking at it, then that gives you the percentage of what was there before increasing each time. So the percentage is the same. All right, so let's take a look at these problems right here. The first one, the average annual population of a pack of wolves increases each year by 25 wolves. So the first year you add 25, the second year you add 25, the third year you add 25. Well, that sounds linear, and in fact, it is linear, right? Now, the value of a coin collection has increased by 3.25% annually over the last 20 years. Now, 3.25% of what was there before at the end of the year. So the first year, at the beginning time, let's say there's just, let's just say there's $100. So at the beginning, we have $100, and this is going to be when t equals 0. And then the next year, it increases by 3.25%, which is $3.25. So we have $103.25 at the end of t equal 1. Now, the next time, it increases by 3.25% again, but 3.25% of what was there the last time, which is this amount. So I'd have to take my calculator to figure out what that is. But basically, it's a percentage of what was there before, which means that this one must be exponential. So anytime it's increasing by the same percentage year over year, or time period over time period, that's exponential. Let's take a look now at the next one. The population of bacteria decreases by a factor of 1/4 every 24 hours. So time equal 1, let's say we've got, 100 bacteria. And then 24 hours goes by and it's decreased by 1/4. So we've lost 25 of them. Now we're down to 75. The next one 4 hours goes by and I lose another 1/4, but 1/4 of the 75. Gosh, that sounds like I'm basically losing 25% each time. This becomes exactly like the one we just did. The percentage decrease is 25% each time, which means that this must be exponential. Population growth of bacteria, people, the spread of diseases, these all tend to be exponential functions. So I was sort of predisposed to know this was exponential because it's the population of bacteria. Now, the next one says, for the first 6 training sessions, a personal trainer charges his clients $5 less than the previous training session. So let's just pretend that I have no idea. Let's say that he charges $80 an hour. So at time equals 0, the very first session, it's 80. And then the next one will be 75. And then the next one will be 70. And then the next one will be 65. And the next one will be 60. He's subtracting 5 each time. It's the same amount every time. Whereas in these over here, it's a different amount each time. All right. So when we're looking at this one right here, the increase wouldn't be another 325. It would be 3.25% of 103.25 added to 103.25. Let me just go ahead and figure out what that would be so that you can see what we would get. This would come out to be 106 basically 61. And that's when t equal 2. So you can see that we added more than 325 because I had some there already. So the amount of increase is changing each time. All right, now let's go ahead and mark this one as linear, and let's consider this last one. The population, when they say population, I immediately think, ooh, probably exponential, of a certain country at time t is represented by this function. Well, let's see if we can get this function into our normal form, a times b to the x. And again, you don't have to, but I think it's a good idea to put parentheses around the exponential part, reminding you that you have to do the exponential before you can do the multiplication by a. Well, this looks like this 50,000 is my a. It looks like this 1.02 is my b. And it looks like the time period up here, that's my x, 0.25x. So I've got a 1.02 as my growth factor. And this one is going to be exponential. Right? So hopefully this made sense to you. Let's move on to some other ones that are very similar. Now, before I continue, I probably should talk a little bit more about this last one. The power is not exactly t like we were expecting, and some students get thrown by that. Does that mean it's still exponential or not exponential? Does it just have to have the variable in the power somewhere? No, it actually has to be linear. So when we're looking at this right here, let's think about, and I'm just going to take out the 1.02 being raised to the 0.25 t power. Now, when I look at that, remember the exponent rules mean that if I have 2 powers that are multiplied together, I actually can apply one at each one at a time. So I could rewrite this instead as 1.02 to the 0.25 power, and then I could raise this whole thing to t. In other words, what I've got here is 1.02 to the 0.25 power, which is a totally different number. And that's actually what my base is. So, but most of the time we consider the growth factor to be 1.02. And the time period in which it's changing is 1/4 of whatever a normal time period is. So if t is in years, then the pattern is changing quarterly, basically. So then we would have 1.02 raised to the 0.25, which, well, it's a really long number, but this would give me 1.004962932 raised to the t. Okay? These would have exactly the same graph. But again, typically we leave it in the original form. And again, what this basically is this is, of course, an exponential because the variable in the power is part of a linear function. Now, it has to be linear. If it's squared, it's no longer exponential. If it's 1 over x, it's no longer exponential. It's got to be a constant times x or t, or constant times x or t plus another number. All right, let's now move on to problem number 2. We want to consider a situation where for each year t, the number of trees in forest A is represented by the function a of t equals 100 times 1.015 t. Now the 1.015, let's talk about what that means. All right, so when we look at this, we have forest A. And we have a of t equals 100 times 1.015 raised to the t. Now, what is this growth factor? The growth factor is the base of the exponential. T is, of course, linear, so we know it's exponential. The coefficient is our lowercase a. So we have lowercase a is 100, and we have the base b equal 1.015. This tells me, because it's greater than 1, that it's increasing, it's growing. So I'm not sure which way I need to go to have you guys going up, but basically, as x increases, then y increases. As long as the base is greater than 1, it increases as x increases, or t in this case. This 1.015 actually means that the 1 says whatever was there before is going to be there the next time, plus I'm adding 1.5% each time. How did I get that? Well, I took the 1.015 and I thought of this as 100 and 1.5%, right? So the 100 means whatever was there before is still there, plus I've added 1.5% every time. So the amount that's going to be there is actually increasing each time. It's not the same every time. It's 1.015 of what was there the previous time. Now in forest B, we have a different equation. In forest B, we have b of t equal to 89 times 1.025 raised to the t. So this 1.025 is actually 102.5%. In other words, what was there before is going to be there again the next time, plus another 2.5% of the previous value. So when I increase each time, 2.5% is going to give me more and more and more as the numbers go up and up and up. This is the joy, the beauty of compound interest when you're investing money. Now, what about these A values? This A is an 89 and this A is 100. What does that mean? Well, when t equals 0, any positive value raised to the 0th power is the number 1. So this means that there were originally, well, 100 trees. So the initial value is 100 trees in forest A, and the initial value is 89 trees in forest B. So this says which forest population is growing at a faster rate. Well, I need to compare the 101.5% and the 102.5%. Forest B is growing faster. Now, which forest had a greater number of trees initially? When I'm looking at that, then I'm looking at the initial value, which is lowercase a. Forest A had 100 trees to start. Forest B had 89. So this would be forest A. Initially, by how many trees did the larger forest exceed the smaller forest? Well, 100 minus 89, that's a 9, not a 1, equals 11. So this would be 11. Which forest will have a greater number of trees after 30 years? I don't know this by inspection. This is something I actually have to compute. So after 30 years, forest A is going to have A of 30, which is equal to 100 times 1.015 to the 30. Now, you want to grab your calculator. Now, when you put it into the calculator, do the exponential part first. Now, most calculators know that it has to be done that way, but be careful how you enter it. Personally, I enter it as the 1.015. And then you're looking for a button that looks like y to the x. You can see right there in the middle on the far left-hand side, it says y to the x, or it might say x to the y, or it might be a caret symbol. So then we're going to hit that button, and it puts it up into the power, and I'm going to put in 30, right? So when you're looking at my screen, you can see now that I've got 1.015 to the 30th. I'm forcing it to do the order of operations. I get a value, and then I multiply that by 100, right? And I'm going to round off to, I think, 2 decimal places is what they're looking for. So, but I'm actually going to carry more just in case. So I have 156.308022. So I have about 156 1/3 of a tree. That doesn't make sense, but you get the impression. Okay, now after 30 years, how many trees does forest B have? It started with fewer trees, but it's growing faster. So this time we have 89 times 1.025 raised to the 30th. So compute your value again. Now this time I'm going to do it slightly different. I'm going to put in 89 times, and then I'm going to put in 1.025, hit the y to the x key, and enter 30. So you can see what it looks like. I use the sharp right view. I think it's the best scientific calculator on the market. It works really well for me. This should follow the order of operations, and it gives me 186.6835145 ... and keeps going probably. So when I'm looking at this, which forest has more trees now after 30 years? The growth rate really causes it to grow. Remember, when you're looking at that graph, well, then it's really going fast, right? So it's just shooting off. As x goes to the right, this goes to the right. Okay? So when we're looking at that, that means that forest B has more trees. And now I take my 186.683, so forth, and I subtract 156.308022, never round in the middle, and I come up with 30.375, blah, 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 rounding to 2 decimal places. I have 30.38. This brings up a good point with exponentials. If you round at middle steps, you're going to be way off by the time you get to the end, because these grow so incredibly fast. Never, ever round. What you want to find on your calculator is a store and recall button. So the store and recall buttons are down here on this calculator. You can see STL and RCL, that stands for store and recall. And then you just enter in one of the letters, all right, the A, B, C, D, right? And then you can store and recall the value. Okay, let's move on now to the next couple of problems, which again is asking, are these exponential growth, exponential decay, or neither one? So let's look at problem 3. We have y equal 4 times 1.2, which is being raised to the x power. This is exactly in exponential form from the get-go. Our a is equal to 4. Our b is the growth rate of 1.2. Because it's bigger than 1, it is growing. As x increases, the y value increases. So it's like this. And we have x, which is a linear function. So this one is definitely exponential growth. right? Let's take a look at this one down here. We have y equals 279 times 14 minus t to the 5th power. Well, one of the key things about an exponential is that the variable, the independent variable, is in the power. And this time, my independent variable is not in the power. This is actually a polynomial function. So it is not exponential growth or exponential decay. It's neither one. It's a polynomial. Now, how would I know that I have growth versus decay? Again, if b is greater than 1, it's growth. If b is between 0 and 1, so a proper fraction, then it's decay, right? Let's move on to problem number 5 now. Looking at problem 5, it again asks, is this exponential growth, exponential decay, or neither one? So let me write out this problem. At first glance, it looks like it might be exponential with an initial value of 18.9 and a growth factor of 1.135. But look at that power. Look at this power up here. That is not linear, right? This is not a line. 1 divided by x is a rational function, which we've just completed studying. So you know that this is not actually exponential. It is something totally different. Let me graph it for you, and then you will know for sure, you can tell that it's definitely not. Now, you do have to be careful because there are some functions that look like this, but are not actually exponential. So just because it looks like this, or opening down, does not actually make it exponential. So you got to be a little careful about that. But in general, they look like that. So let me take a look and I'll graph it for you. So now what we can see is we see this graph right here. Now it almost looks like a rational function that's been shifted up. But notice that this one does not go down forever. So it's not even a rational function. It's just something different, right? But it clearly does not have a typical exponential shape. Now let's take a look at another type of problem. What if we know 2 points and we know it's exponential, but we don't know the equation? Can we find the equation? As long as you have 2 points and you know it's exponential, you should be able to come up with an exponential function that includes those 2 points. And you can see right here that it has steps on how to do that. Now, if one of your data points is 0, a, then that's the initial value. When the independent variable x or t is 0, then the other value has to be the coefficient of the exponential, lowercase a. Now, if you don't have that, then you're going to have to write 2 different exponential equations using the ordered pairs for each one, where one, the x value is the power and the y value is coming out to be the result, because it's f of x equals a b to the x, and f of x represents y. And then you have 2 equations and 2 unknowns, so you can solve the system. Let's demonstrate this method now using this problem right here. So I have 2 points. I have the point 0, 5, and I have the point 1, 1, but it's not linear, it's exponential. So I know my equation has to be y equal a times b to some power x. Now, when x is 0, b to the x becomes 1, and that gives me a. So I know automatically, because this one has 0 for the x coordinate, that the y coordinate has to be lowercase a. So a equals 5, right? Now I need to use the other point. I've used one of the points, but I've got to use them both. It takes 2 points minimum. So what I want to do is I want to write my equation as much as I know, which is a times b to the x, but I know that a is 5, so I have 5 times b to the x. All right, so if I have 5 times b to the x, I know that the other ordered pair is on the exponential function. So I know that when I substitute 1 for x, I get 1 for y. So I'm going to replace the y with 1, and I'm going to replace the x with 1. And this gives me 1 equal 5 times b to the first. Well, b to the first is just b. So I get 1 equals 5b, which tells me that b is equal to 1/5. And this would be an exponential decay because the base is between 0 and 1, a proper fraction. So then I rewrite the equation, y equal 5 times 1/5 to the x. Now, a lot of students on this one, they're like, oh, well, then the 5s cancel. No, no, no. You have to take 1/5 to the power first. It's not going to be 1/5 anymore. And then you multiply by the 5. You cannot multiply the base times the coefficient until after you have done the exponential. All right, let's move on to a very similar problem. This is problem 7, doing the same thing, but this time we weren't given the initial value. So we have 2 ordered pairs, -4, 5, and the ordered pair 4, 1. Now I know that both of these are on my exponential equation, and my exponential equation is a times b to the x. So I'm going to use each ordered pair to write an exponential function. So using the first, I have 5 equals a times b to the -4 power, right? So that's one exponential equation. We can call that equation 1 if we want to. And the other one, when y equals 1, then the power b is 4, or the power on b is 4. So I have 1 equals ab to the 4th. Now, looking at these two right here, I'm like, oh, I don't really know what to do with this. Well, I've got 2 equations, equation 1 and equation 2, and I have 2 unknowns, a and b. As long as I have at least as many equations as I have variables, I can solve for the values exactly. So what I'm going to do is I'm going to take each of these equations and I'm going to rewrite them in a form where I can solve for a. So the first thing I'm going to do is I'm going to take equation 1 and I'm going to rewrite this as 5 equals a divided by b to the 4th. Remember, a negative exponent changes position. It's written in the numerator, so it changes to the denominator now with a positive power. Now I can take this and I can solve for a. And notice I'm not putting equals in between the equations, I'm putting arrows. When you rewrite the entire equation, put arrows in between, not equals. And then this gives me a equals 5b to the 4th, right? I'm going to call this one equation 3. That's my new equation. Now I'm going to take equation 2 and I'm going to solve for a again. I need to solve for the same variable. So this one is 1 equal ab to the 4th. So all I really need to do is divide by b to the 4th. And that will give me a equals 1 divided by b to the 4th. And I'll call that equation number 4. Now, if these are the a values, the a value in the exponential is the same a, so they have to be equal to each other. So I'm going to set 3 equal to 4, and this is going to give me 5b to the 4th equals 1 divided by b to the 4th. Okay, you may be going, this is long. Yeah, it's kind of long. All right, next thing we need to do, remember b cannot be 0. Bases have to be strictly positive, not 1. So it can't be 0, so we don't have to worry about that being a problem. And I'm going to multiply both sides of the equation by b to the 4th to get all of my b's together. Right, so this is going to now give me the equation 5b to the 8th equal to 1, right? So that moved all of my b's to the left side. Now I want to isolate b. So the first thing I'm going to do is I'm going to divide by 5. So this gives me b to the 8th equals 1/5. And then, yes, I have to take the 8th root. So this then gives me that b is equal to, and remember, 8th root, normally we think of a positive or a negative, but b has to be strictly positive. So this is going to be the 8th root of 1 divided by 5. Remember, you can split the radical. So this becomes the 8th root of 1 over the 8th root of 5. And the 8th root of 1 is 1. So we get 1 over the 8th root of 5. That's B. It's not a nice number, but it's a number, right? Okay, now you may be going, well, that's great, but I don't have A. Okay, well, I can find A by using either equation 3 or equation 4. Either one will work because it's the same. So in this one, I'm going to use equation 3. So I need a little more space, looks like. Let me create just a little bit more space here so that I can keep writing. So now I'm going to take equation 3, and I have A equal 5 times 1 over the 8th root of 5 raised to the 4th power. Now you may be going, well, I don't know how to do that. Yes, you do. Remember that when we have an 8th root, that means the 1/8 power. So I have 5 to the 1/8 power, all raised to the 4th power. Well, 1 to the 4th power is 1. And this gives me 5 to the 4/8 power. And the 4/8 power is the 1/2 power. So this gives me 5 times 1 over 5 to the 1/2, which is really the square root. But again, I've got 5 over 5 to the 1/2, so I can subtract the powers. 1 minus 1/2 is 1/2. And I basically end up with 5 to the 1/2, which can also be written as the square root of 5, right? So now I'm ready to write my equation up here. So I have y equals, or f of x equals, and it says in the form y equals, so we'll put y equals the square root of 5 times 1 over the 8th root of 5 raised to the x power. Now, if you're wondering how to put this into a system, sometimes you can use the caret symbol. You could rewrite this right here as 5 to the negative 1 over 8 power, right? Because the negative moves it to the numerator, and then the 8th root is the 1/8 power, right? So it can be written like that. And sometimes you use the caret symbol. Be sure to put parentheses around the 1 divided by 8, right? So sometimes in some systems, it's going to look like this, negative 1 divided by 8, right? So it would look like that. Right? Okay, let's move on to the next problem, which is problem number 8. And this time we're not given the equation. This time we're given the table of values, and we're asked to determine whether it's linear or exponential or neither one. So these are much trickier. If it's linear, it's pretty simple to see. If it's exponential, it is not simple at all right? And then, of course, we have to eliminate both linear and exponential to come up with the solution of neither. If it is exponential or linear, then they want us to come up with the equation for it. So when we're looking at this one right here, the first thing I always look for is linear because it's the easiest. So my first y value is 70. Notice x is increasing from 1 to 2, so a change of 1. We need a change of 1. And then 70 goes from 70 to 40. So that if I'm looking at linear, I'm looking to add or subtract the same value each time. That's subtracting 30. Then 2 increases by 1 to 3, and it goes down by 30 again. And then it increases from 3 to 4 by 1, and it decreases by 30 again. It's got to be linear. So I'm looking at this one, it's linear, and my rule is subtract 30, right? Which is basically giving me the slope. All right, so what do I have? Well, I've got lots of ordered pairs. I just need the equation of a line. So I've got the ordered pair 170, and we'll just do the next one. I've got the ordered pair. Well, let's do the ordered pair 3, 10. Those numbers are a little easier to work with. I need to find a slope, which I'm expecting it to be negative 30. So I'm going to do change in y over change in x. So I'm going to do 70 minus 10 on top. But once I choose 70 to go first, its x value, which is 1, must go first on the bottom. These two have to line up right here in the same ordered pair, and the second two have to be out of the same ordered pair. So this is going to give me 1 minus 3. So that's going to give me that negative that I'm expecting because it's decreasing. So this is going to give me 60 divided by negative 2, which is exactly what I thought it would be, negative 30, because I'm subtracting 30 each time. Now I need the y-intercept. So I can take any of the points. I'm going to use 3, 10. And I'm going to write y equals negative 30x plus b. And I'm going to use 3, 10. And this means when y is 10, the x was 3. And then I'm going to solve for b. So this gives me negative 90. So I have 10 equals negative 90 plus b. So I add the 90 and I get b equals 100. Okay. So this is my line, y equals negative 30x plus 100. And it did say to write it in slope-intercept form, and that's what we have. Okay, let's move on to the next problem, problem number 9, which is essentially exactly the same as the previous problem. So go ahead and pause the, well, actually, let's not pause, because this one's going to be harder, and you'll probably need a little bit of help the first time. All right, so when we look at this one, the first thing we look for is linear, because that's the easiest. 70 decreases to 49 by subtracting 21. But if I subtracted 21 again, I should get to 28, and I've got 34.3. And then from 34.3 to 24.01, well, that's definitely not the same value. So it is not linear. So I already know that it is not linear. So it's either exponential or neither. So the question is, well, I mean, I could find the equation. I'm going to have to find the equation if it is exponential. But the question is, how do I know it's exponential? Well, if I'm looking at these each time, the question is, am I multiplying by the same value each time, or subtract or dividing by the same value each time? So if I take my 49 and I divide by 70, I get 7 over 10. So what I'm actually asking is, what percent of 70 is 49? Now, if you're asking that question, you're asking, is it changing by the same percentage each time? The percentage means that it would be exponential. So let's translate this into our equation. What percent is going to be our unknown? So we'll let this be, oh, I don't know, let's let it be P. Of means times, so I have 70P. Is equals, so I have 70P equals 49, which basically means to get the percentage, I'm going to divide 49 by 70. So I divide the next one by the previous one. And when I divide this out, I get 7 over 10. All right. Now, that means to go from 70 to 49, I multiplied by 7/10. In other words, it was a change. All right. So I had a decrease here. All right. So of 70, 30%, a decrease of 30, but changing to 70% still there. All right. So the next thing I want to do is I want to find out if the 34.3 has the same relationship to 49. And unfortunately, with exponentials, you got to check all of them. So this is going to be what percent of 49 is 34.3. So this becomes 49P equals 34.3. So the percentage is 34.3 divided by 49. And when you do that, you're going to get 34.3 divided by 49. Aha, 7/10. So this tells me that I am using the same multiplicative factor between the first three. Now, what about that last one? Just because the first three work doesn't mean the last one does. You have to check. This time we're going to shortcut, and we're just going to do 24.01 divided by 34.3. So punch that into your calculator. And you get 7/10. That means that we have a base of 7/10. That's what's being multiplied each time, all right? And we don't know the initial value because we don't have the x equal to 0. So we don't know what the initial value is, but we know our b is 7/10. Again, you can go ahead and take the values. I would probably use the 1 and the 70. And I would use the 2 and the 49. And you can solve this as we did the previous ones in order to find the equation. So why don't you pause the video, work that out, then turn the video back on, and we'll compare our solutions. Okay, so how'd you do? Let's compare our answers. So I went ahead and solved it. I didn't use the information that I already knew that the base has to be 7/10. I solved it like I did before, using the ordered pair 170 and the ordered pair 249. I wrote two equations that were in exponential form. Then I solved each for A. You could solve for B, but B is squared in the second, so it's much easier to solve for A. Then I set them equal. I got all the b's on one side and I got the constants on the other, and I got b was 7/10, which I knew it was going to be because that was the percentage, right? So that was what was changing each time. That was the multiplicative factor. Then I used the first equation here, a equals 70 divided by b. And I took this a equals 70 divided by b, and I substituted b as 7/10. Now this gives us 70 divided by the fraction 7/10. So to divide by a fraction, you take the reciprocal and multiply, and the 7s cancel. I get 10 times 10, which is 100. So my equation is 100 times 7/10 raised to the x. Let's move on to the next problem, which is exactly the same. So when we're looking at this one right here, we're going to be solving the same problem, deciding whether this is linear, exponential, or neither. Let's go through it and see if it's linear. That's easier to do. 80 to 61 is a difference of 19. But 61 to 73, wait, that went back up again. So that doesn't make sense. That's not linear. And then it goes to 52. It's definitely not linear. Could it be exponential? Let's take a look and see if we think it could actually be exponential. So when we're looking at this, the first thing I want to do, since I know that it's not linear, I want to check for exponential. So I take the one after, which is 61, and I divide by 80, and I see what my common ratio is. And this is going to give me an exponential multiplicative factor if it's exponential. And this gives me, well, 61 divided by 80 doesn't reduce, so I can just leave it. What about the next one? Well, that's 73 divided by 61. This one is, first one is less than 1. The second one is greater than 1, but the main point is they're not the same. And if they're not the same, it's not exponential. And that means that it must, in fact, be neither, which means we don't have any work we have to do. It's not either one. And if we were to plot something like this out here on the graph, we've got x equal 1, 2, 3, and 4. And it looks like I need to go from 50 to 80. So let's go by 10, and then 20, 30, 40, 50, 60, 70, 80. So when x is 1, I get up here to 80. 2, I'm at 61, which would just be about here. And at 3, I'm at 73, which would be up a little bit. And then at 4, I'm at 52, which would be down. You can tell that this is zigzagging, all right? And because it's zigzagging, it is not exponential or linear. Let's move on to the next problem. Same type of deal. This time when I look at it, I see that I go from 10 to 20 to 30 to 40. I'm adding 10 every time. Okay, it's got to be linear because I'm adding the same value each time. In that case, that means that my slope is probably going to be 10. So I'm going to take two ordered pairs. I'm going to use 110 and 220, and I'll verify that it is 10, but that's what I'm adding each time. So that should be the slope value. So slope is equal to y2 minus y1 over x2 minus x1. So let's do 20 minus 10 on top, and then what belongs with the 20 is the 2, so it has to go first on bottom, and the 1 belongs to the 10. Those have to go together. And this is going to give me 10 divided by 1, which is what I expected, because this is plus 10 plus 10 plus 10 to get from one to the next to the next. Now, I don't have my y-intercept, but if I'm adding 10 each time, can I go backwards? Yes, I can. So if I had this, the next one in front of it would be the 0, and that is when I get the y-intercept. So subtracting 10 would give me 0, meaning it goes through the origin. So this must be the function 10x. Now, if you're not sure how I did that, don't forget that you can just take the equation y equal mx plus b, replace the slope with 10, and then use one of your ordered pairs. I'd probably use the 110 since the numbers are smaller. Y is 10 when x is 1. And then the only thing that will make this true is if b is equal to 0. And that means it goes through the origin, right? Let's move on to the next problem, which is going to be using the compound interest formula. Okay, so let's talk a little bit about the compound interest formula. This is when you invest money into some savings account or CD, and it's earning a certain interest rate per year, and maybe it's being compounded a certain number of times a year. In other words, the compounding is when they go in and they compute the interest earned so far that year, and then they add it into the account. So let's say you start with $1,000 and they compound it quarterly, which means at the end of March and the very beginning of April, they're going to go in and there's $1,000 in there. So they're going to say, okay, the interest rate applied to the $1,000 adds, well, I don't know what it adds. Let's say it adds $5. So then on April 1st, you have not $1,000, but $1,005. And then the $1,005 sits there from April, May, and June. And the very end of June, on the 30th, they go in and they say, well, what was the same percentage? What's the same annual interest rate applied to the $1,005? So then you get the same interest on the 1,000, plus you get the interest on the $5 that got added at the end of the first quarter. And then that becomes the amount you have the next day. So let's suppose that that's $5.50. So on July 1st, you have $1,000, I'm losing track, $1,010.50. So the next time they go in and compute the interest, you're going to get even more interest. So it compounds, it increases each time. Now let's take a look at the formula here so that we can understand what it is. It's a complicated formula, and you need to be super careful about the order of operations. So I'm going to go through this very carefully. So this is A equals P times 1 plus R over N to the NT. Okay, all right, what have we got here? A is the account value at the end of the time period, the accumulated amount. That's the way I think of it, A for accumulated amount. What's P? That's your principal or present value. That's what you originally put into the account. That's the $1,000, all right, that you invested on January 1st. R is the annual interest rate, often called the nominal rate, right? So it's the annual interest rate. Right now, maybe 4% or something like that. So that would be 0.04, and it's divided by the number of compounding periods in the year. If it's quarterly, that means at the end of March, at the end of June, at the end of September, and then at the end of December. So that's 4 times a year. So quarterly means that n is equal to 4. Annually, n would equal to 1. And we don't usually call that compound interest because it's only changing once a year, but yes, you could consider it compound. Semi usually means twice. So semi-annually means it's changing twice a year. So that means they go in on June 30th and December 31st. Monthly, of course, n equals 12. Now, daily in banks could be anywhere from 361 to 365. I don't know why, but they use different values. I don't know if they're just taking a few holidays or what it is. But for our class, we're going to use n equals 365. All right, it's actually 365 and a quarter because of the leap year every 4 years, but we'll go with 365. So this is what we have right here. Make sure that when you put in the R, that you use the decimal. So 4% becomes 0.04. This is the one that you want to use in the formula. So if I invested my $1,000 and it was quarterly and the interest rate was 4%, then I can come in here and I can write my $1,000 principal times my 1 plus 0.04 divided by 4 to the 4 times t. Now, the 4t is, of course, a linear function, so it is an exponential. And this 1 plus 0.04 over 4 is giving me the growth factor. It is a growth because it's going to be bigger than 1. The 1 means that what was there before still stays there. And this is actually the amount of increase. So when I'm looking at this, all I need to do is figure out the number of years it stays there, and then I'll know what the accumulated amount is at the end of that time period. Let's take a look at problem number 12, and let's see if we can figure out the solutions. So an investment account is represented by this formula right here. So this means that I originally invested $19,455. The 0.029 is the interest rate, which is 2.9%. The compounding periods is 12, which means it's monthly, right? So at the end of every month, they go in, they compute the interest on what's in there from the previous month, and then they add the interest in. So on the first day of the next month, there's more money. And then at the end of that month, they compute the interest on what was there on the first of the month, which includes the interest from the previous month. How much money is in the account at time t equals 7? So what we need to do is we need to plug in 7 for t. So 12 times 7 comes out to be 84, I think. So we want to find A of 7, the accumulated amount after 7 years. And this is going to give us 19,455 times 1 plus 0, oops, that's a plus, 1.029 over 12 to the 84th. Now, parentheses trump everything. Remember, the order of rate operations follows mnemonic PEMDAS. So parentheses trump everything. Inside the parentheses, division comes before addition. So the first thing I'm going to do is I'm going to do 0.029 divided by 12. 0.029 divided by 12 equals, you got a number. You should have 29 divided by 12,000. Now add 1 plus 1 equals. Okay, this becomes your base. And then you're going to raise it to the 84th power. So either y to the x, x to the y, or the little housetop symbol, caret. So I'm going to hit that, and I'm going to raise it to the 84th equals. So you should now have 1.224772488, blah, blah, blah. Now I multiply by the 19,455. The principal, the initial value, is always the last thing you multiply by. So times 19,455 equals, and this is an approximation because it goes many decimal places, but this is money, right? So we're going to round to 2 decimal places, and I get $23,827.95, right? So this gives me the value that I would put in here. So this is money, but you probably don't need to put in the symbol in the system. Okay. Now, what is the principal value? We already said that's 19,455. And we already entered the interest rate. They want it as a percent. And don't forget the symbol. So this is 2.9%. All right, let's move on to the next problem, which talks about continuous compounding. Now, continuous compounding, now you know if you're looking at this right here, that monthly is probably better than quarterly, which is better than semi-annually, which is better than annually. Daily would be better than all of those. But what if you were doing it at every possible moment in time? Do we have some limiting value if the number of compounding periods n goes to infinity? And the answer is yes, we do. When we do that, we end up with Euler's number, which we use the letter E, an italicized E. So this becomes Euler's number. Now, Euler looks like Euler, but it's pronounced Euler. It's a German name. He lived in the German part of Switzerland. Leonhard Euler is one of the most famous mathematicians, super brilliant, did astounding work well into his 70s and 80s. And he was blind the last 20 years of his life, but he was just as prolific. He just dictated everything and did it in his head. It's just amazing. Okay. So it turns out that the limiting value for the interest rate, if we take 100% and we let n go to infinity, then this approaches the number e. Now, e is irrational, and that means it cannot be written as the ratio of 2 integers. As a decimal, it never repeats and it never stops, right? That's irrational. So they only gave you a few of the digits, but I'm going to give you more. So it's 2.7, 1828, 1828, which always makes students think, oh, it repeats. No, it doesn't. From there, it goes off 4, 5, 9, blah, blah, blah. So it does not have a pattern. There's no pattern. So it's about 2.72 roughly, right? So this is Euler's number. So it replaces all of that 1 plus r over n to the n on the inside. And we end up with this formula right here, which is the continuous growth or decay formula, which is the accumulated amount becomes the initial value a times e to the rt power, right? And I like to write it like that. Now, if we're talking about continuous compounding with money, then the initial value is written as P for principal, the original value, the present value. So we get P e to the RT, which looks like the word PERT. And again, I like to put parentheses around the e to the RT to remind you that you have to do that first before you can multiply by the initial value. Now, A again or P are the initial values, R is the continuous growth rate per unit of time, and T is the elapsed time. Now, this is what happens for most population growths. They're continuously growing, right? Population's growing at every possible moment in time. So this formula is typically used to describe population growth. Now, R is what's called the continuous growth rate. So it's growing at some rate. If R is positive, then it's growing. If R is negative, then it's actually decreasing. So it's coming down in value. But the amount is still going to be positive because E is a positive number being raised to some power. The power can be positive, negative, 0, it can be anything, but the base has to be strictly positive and not 1. All right, let's look how to use this formula. We have the equation 333 e to the negative 0.78t, which is of the form a times e to the rt. So the r value for the equation is the negative 0.78, right? And this type of change is a decay because r is negative. So the r value here is negative 0.78, and it represents exponential decay because r is negative, right? So hopefully that makes sense to you. If r is positive, then it's going to be growing. If r is negative, it's going to be decreasing, right? Okay, let's take a look at this problem right here. Y equals 39e to the 0.71t. So our growth factor here, our growth rate, R value is 0.71, which is going to be exponential growth. Because it is positive. So in this case, they're typically going to be less than 1, not necessarily, but often, because r is positive. All right. So now we want to look at this equation, and we want to do the same thing we've done before. So go ahead and pause the video, then turn the video back on, and let's compare our answers. So compare your answer. How'd you do? All right, good job. Now let's look at this one right here. This one has 8 times negative 7 raised to the x. Find f of negative 2. Now the question is this exponential, or is this just some other kind of function? Well, I've got a negative 7 as the base. That's not allowed, which tells me that this is not exponential. It's a function, it's just not exponential. So when I look at this, I can still find f of negative 2. I'm going to take f of negative 2 equal to 8 times negative 7 to the negative 2. Now, this is the same thing as 8 times 1 over negative 7 to the positive 2. Remember, a negative exponent changes position, numerator to denominator, and vice versa. Then I square the negative 7 to get 49. So I get 8 divided by 49. Now, this is not an exponential function because the base is not allowed to be negative. All right, so they're trying to trip you up a little bit here. Let's look at this one. Do you think this one is exponential? So I've got 5 to the 2x minus 3. Find f of 1. Well, 5 to the 2x minus 3, 2x minus 3 is linear. So it is, in fact, an exponential equation. And when I look at this particular one, if I plug in the value x equal 1, I get 5 to the power 2 times 1 minus 3, which gives me 5 to the 2 minus 3, which gives me 5 to the negative 1, which gives me 1 over 5. And it is exponential, right? Okay, let's move on to the next one, and we'll decide if we think this one is exponential or not. I've got 3.8 at the front as an initial value. I've got 1 for the base. Whoa, now exponentials, the base has to be strictly positive and not 1. It's not exponential, right? So when I'm looking at this one, 1 to any power is actually 1. So I'm thinking this is probably just a constant function, which sounds kind of crazy, but let's check it out and see. So f of 3 is going to give me 3.8 times 1 being raised to the negative 3 plus 1, which gives me a negative 2 power plus 2.5. 3.8 times 1 to the negative 2 plus 2.5. The negative power sends it to the denominator, opposite location. So I'll put parentheses, 1 over 1 squared, but 1 squared is 1, so it's still just 1. And this gives me 3.8 times 1 plus 2.5, which comes out to be 6.3. All right, it is in fact linear. All right, it's tricking you a little bit. The negative x plus 1 is linear, so you might be thinking, oh, well, it's got to be exponential, but the base is 1, and that means that it's actually going to not be exponential. Okay, let's take a look at problem 19. The fox population in a certain region has a continuous growth rate, continuous. When it says continuous, then you know you have A as a function of t is equal to A e to the RT power, or PE to the RT if you're doing money. So we have some initial value e to the RT. So when I'm looking at this right here, this continuous growth rate of 3% tells me that R is going to be 3%, which is 0.03. So I know that's my continuous growth rate. It's positive, so it's growing. In the year 2012, there were 23,130 foxes in the area. Write a function f of t that models the number of foxes in the population t years after 2012. So let 2012 be year 0. If that's the case, then the number of foxes in that year is my initial value. So A is equal to 23,130. So now I have that the accumulated amount later on is going to be 23,130 times e to the 0.03 t. And this becomes my equation. Now, the next question is, what is the fox population predicted to be in 2020? You're not going to plug in 2020. You need to figure out how many years are between 2020 and 2012. So you subtract and you get 8. So 2020 is 8 years after 2012. So t equals 8. So we want the accumulated amount after 8 years. So we have 23,130 times e to the 0.03 times 8. And now what are you going to do? You have to do the exponential part first. In the power, you're going to have to do the 0.03 times 8 first. So one thing you can do on your graphing calculator, you have an e to the x button. So mine is, I don't know if I can keep that there, but I'll try to close it over here. I lost it. Okay. Can you see the e to the x? All right. So above, in my case, it's above the ln key. So above the ln key, you have e to the x. So I hit second and then ln, and that gives me e to a power. And I'm going to put in 0.03 times 8, and then hit equals. So I got 1.27124,915 times, last thing I do is multiply by the initial value, 23,130. And I came up with approximately 29,403.99285, so 0.99. So roughly 29,404, right? Not quite that last box, but pretty close. All right, I think we only have one problem left to do. So let's take a look at our last problem, and then we'll be able to move on to the next section where we talk about the graphs. So Adam wants to save $47,000 for a down payment on a home. how much will he need to invest in an account with 8.3% annual percentage rate, that's the nominal rate, compounding daily, we're going to use 365, in order to reach his goal in 6 years. Whoa, okay. Well, compounding daily isn't the continuous, so it doesn't use the E. So I must have this other formula, A of t equals the initial principal times 1 plus the interest rate as a decimal divided by the number of compounding periods times the number of compounding periods times time. That NT is actually how many times they go in and compute the interest, right? So if it's 4 times a year, 2 years, that's 8 times they went in and computed the interest. So, what do I know? Well, he's not investing $47,000. He wants to save $47,000. So that's what he wants at the end. So that must be A of t. So A of t, and he wants to do this in 6 years. So A of 6 needs to be $47,000. After 6 years, he wants $47,000 in this account. Okay, well, I know it's 8.3%, so R equals 8.3%, which becomes 0.083 as a decimal, compounded daily. So we're going to use 365. All right, and we want to round to the nearest penny. Do I have everything I need? I think I have everything I need. I know T is going to be 6 years. The only thing I don't know is P. Well, that's what they're asking. How much money does he need to put in today so that he ends up with $47,000 in the future? So I have A of 6 equals unknown P times 1 plus 0.083 divided by 365 times 365t. And I know my A of 6 is 47,000. Okay, well, I need to work out at least the 1 plus r over n to the nt power. And then I can solve the rest of it for p. So what I actually am doing is I'm dividing the 47,000 by that entire exponential expression. So I get 1 plus 0.083 divided by 365. And t, oh yeah, t was 6. So we should replace that with a 6. 365 times 6. And that will give me p. So this is just another way of writing the equation that solves it for p. Now, what do I need to do first? Well, before I can do the outside division, I need to figure out what 365 times 6 is. And then that's going to be the power on 1 plus 0.083 divided by 365. So I'm going to start on the inside with my 1 plus 0.083 divided by 365. And I get a number, which is about 1.000227397. And then I'm going to raise that by hitting the y to the x, x to the y, or the caret key. And I'm going to do 365 times 6 as my power. And I've got about 1.64533, blah, blah, blah. And I'm going to write at least part of that down, because you want to do this on an exam to make sure that I know that you had some of the interim values right. Now, I'm going to keep everything that's in here. I'm not going to round this off at all. I cannot round into the final answer. But I want this to be in the denominator, so I'm going to store it. So I'm going to hit store, and then I'm going to put it into A. So it's an A. And then I'm going to do 47,000 divided by recall A, and I get the following amount. So this becomes the principal I need to invest today is roughly $28,565.63. right? If you invest that today, then in 6 years at that interest rate, you'll have $47,000, which is pretty amazing. All right. I hope this helps, and I hope that you will join me for the next video in the series.